Hello, I'm Dave Brains from IBM Research UK, and I'm going to give a brief summary of our research under the DAIS ITA that is focused on enabling rapidly formed human agent coalition teams through extensible information exchange. I have led this work with key collaboration from Alan Preece and Colin Roberts at the Cardiff Crime and Security Research Institute, but I should also mention that I have received excellent input and advice from many collaborators across DAIS ITA, from ARL, DSTL, Cardiff and other organisations as each of the different use cases have been developed. This environment and the underlying human agent knowledge fusion approach have been used in a number of demonstrations and proof of concept examples showcasing research from other areas of DAIS ITA, especially in cases where the exposure of the agents or their explanations to human users is useful, or where additional human knowledge can be plausibly added in order to improve the performance of the machine agents in this environment. There are currently 8 videos covering about 90 minutes of material since early 2020 that capture different stages of the implementation and highlight different aspects of the human agent knowledge fusion principle that are supported by this work. Some of these are copies of presentations or live demonstrations that have been given at different events. There are also a number of publications that report on these advances, and both of these lists will be updated as new videos or publications are created. Before the end of the DAIS program in September 2021, I plan to release this experimental environment as open source on GitHub. The web address shown on this page contains links to all of these videos and publications, and this demonstration draws material from these to present an overview of the capabilities that are available to be applied to any environment that might benefit from human agent knowledge fusion. The purpose of this environment is to enable fluid and expressive contribution of knowledge by both human and machine agents, directly supporting the tellability and explainability flows that underpin the human agent knowledge fusion architecture. The working name for this experimental environment is CogniSketch, capturing the freedom and informality of sketching, coupled with the ability for human knowledge or AI-extracted information to be captured for situational understanding as well as other use cases. These capabilities are implemented as a knowledge graph with optional semantics and can be rendered or summarized for human users and accessed or reasoned over by machine agents. It is based on the AI Blackboard architecture, where any agent with appropriate permissions can read and write to the blackboard. For our experimental work, we are using relatively small models and datasets, and therefore make use of the basic canvas on which the knowledge graph data can be created, edited, and explored. This does not need to be the sole method for interaction with the data, however, and there are many other forms that will be more useful in particular settings and at higher data volumes, but for the research we're performing, this is a suitable, generic, and extensible environment for that activity. The environment supports access for multiple human users and/or machine agents, with the ability to apply security to access the environment or any node, link, or property within it as needed. Each user can create or access any number of projects, and each project uses a specified palette which contains the user-defined concepts and semantics. These palettes can be shared across multiple projects and users, and can be easily copied and extended as required. Both projects and palettes are simple knowledge graph data, which in this experimental implementation are simply saved as files of data. The environment contains core capabilities and a number of well-defined extension points. These allow anyone to create and embed new semantic models as palettes, new AI agents as functions, or new visualizations as panes. There are other potential extension points within the architecture too. The best way to explain this environment is through demonstration, which I will now do for the remainder of this presentation. These are deliberately generic and have not been tied to specific military situations or scenarios, since this environment is intended to support any use case and any dataset or model can be quickly customized to support new scenarios. This environment features in a number of other demonstrations where the focus is on other research and more militarily focused use cases, so in this demonstration I focus on the capabilities and the underpinning principles, since the whole purpose is to be able to apply these to any situations quickly. As a proxy for open source intelligence analysis, I have used the Simpsons characters for a number of my demonstrations of this environment. This is because it is deliberately non-controversial in terms of subject matter and content, but also because it provides a rich social network of the characters, as well as contextual or layered levels of understanding, for example by stepping out to the content creators and voice actors and their relationships, as well as their connections to the characters. You'll also notice that some of the user interface and layout improves over the series of videos in this demo. Whilst this research isn't specifically focused on usability, it is an important consideration for our basic research and should be good enough for casual human users to use the environment. So let's take a look at some of the basic capabilities. In all of the visuals so far, we've seen basic node creation, extension of the palette, we've seen the timeline view, now we're looking briefly at the map view. All of this is just to give an overview of the general kinds of capabilities that we see as being essential for this kind of human agent knowledge fusion environment, all of which is extensible as needed. One of the extension points within this environment is the ability to easily embed AI agents as functions that can be invoked in context. These can be run locally to the human user or remotely as edge or cloud services, and the creator or developer user is able to define and embed these capabilities very easily with a small amount of code. In this section, I will show some basic language and image processing capabilities that have been wrapped and embedded into the environment, allowing them to be invoked on different content and write their results, including explanations, into the knowledge graph. There are no constraints as to the kind of agents that can be embedded, with the only limitation being what can be written in code, and all agents are able to access the knowledge graph, as well as create or edit nodes and links on it. So here is a quick example of these language processing agents operating. The examples so far have shown various news articles and fact extraction services, so identifying entities and in this case categories from the text that we are processing. In this case we found a PDF, we can drop the URL for that onto the canvas, and we have a very simple PDF extraction agent which will render the full text of the PDF onto the canvas for further processing. So you can see with all of these are agents and humans working together, each of which are contributing their knowledge onto the blackboard, which is the canvas. Here we see some visual analytics, so simple wrapping as machine agents of available services. We're here looking at EXIF data embedded within the imagery, and in that case finding a location. And here we're doing visual analytics, so online services that will attempt to describe the scene. And in all of these cases, the information from the machine agents is being written onto the canvas, and some of the properties include the explanations of what was found and the confidence levels. From earlier research, we know that semantics are powerful additional information that can help inform human users as well as enabling machine processes to improve or refine their capabilities. The ability to add semantics is a great example of tellability within the human agent knowledge fusion architecture outlined previously. So sticking with The Simpsons in this example, I'm going to show the addition of semantics and how it affects copy and paste of text. Now you've seen by dropping the text from the formatted text box onto this Simpsons concept, it creates attributes inside of the node. But let's actually have a look at this. We can see there are different named relationships, so let's actually create these as semantic relationships within our model. So each of these, voices of, developed by, and so on, are different properties which we can create based on what we find in the wild. So this is very informal semantics, but it is meaningful to the machine. So now we can paste that text back onto that concept, having added these semantics, and we see a very different result when we do that. So let's do this action again. So here you can see the machine is now able to create meaningful relationships with named links between the entities just by adding that very simple piece of semantics. And any remaining attributes remain as attributes. The human user can also come in and still add any additional knowledge as they see fit. Conversational agents are a powerful mechanism for interacting with data and knowledge, and currently a very hot topic. The steps we have seen previously show how easy it is to create knowledge in this environment and to add simple semantics. Through provision of a simple chat agent extension, it is very easy to expose the knowledge graph in the form of a conversational agent. Since this is not a key focus of our research, we have performed a minimal implementation for this capability, enabling simple graph traversal and inference using the semantics. But this capability could be substantially improved in the future through fairly simple development, and by maintaining generic capabilities in the chat agent, it is possible to apply this powerful capability to any knowledge graph as it is developed in real time. As the capability has matured, I have supported an open source intelligence investigation which attempted to use this environment for the end-to-end open source investigation process. So this example is around sense making. It mainly exercises the tellability flow and is inspired by the work of Parolli and Card in defining multiple interconnected sense making loops. The image that we start with, it represents an anonymized complex graph that was created as an example of the CogniSketch environment being used for sense making based on open source intelligence activities with colleagues from the Cardiff Crime and Security Research Institute. This graph was created over a period of a few months in conjunction with the development of the platform, with the exercise confirming and identifying a number of key requirements. So here I'll show a few brief snippets of user activity creating a knowledge graph to support sense making, initially in the foraging loop from Parolli and Card. The users identify information in the form of text, images, videos or any other format and bring them into the graph, linking them to other information and creating new nodes or links to capture ideas and potentially missing items. The environment also supports the addition of story elements as a narrative overlay on top of the basic graph, thereby adding more support to the Parolli and Card sense-making loop. There are also multiple views within the environment for tabular data, spatial map interaction and others. I don't use the same domain as the open source intelligence investigation. I instead use IBM historical information to keep things desensitized for this video. In this second example, I refer to the presentation we gave at the AAAI Fall Symposium series in 2020. Here we show the usage of an entity detection algorithm embedded within the environment, creating different instances of detected objects on the canvas. This is then extended through the definition of complex event processing rules to allow the human users to define what a series of simple detections can be interpreted to be. We used a toy example of breakfast events to suit the webcam setting, with rules that are triggered if a person, a cup, and an item of fruit are detected in a short time period. You can see in the video how all of this is supported within the environment and through an extensible palette, new machine agents, AI processes or rule definition languages can be added. In this example we show a breakfast event being inferred as the human user enters the scene and shows the required objects to the webcam. The detected events and matched rules are all recorded on the canvas for later exploration or explanation. So, in summary, I have given an overview of our ongoing research into human-agent knowledge fusion as a mechanism to enable rapidly formed human-agent coalition teams through extensible information exchange. The key flows of tellability and explainability are shown through a number of examples with both human and machine agents creating or consuming knowledge in the graph. The ability to define semantics through shared palettes and the various extension points of this experimental implementation known as CogniSketch have been shown, highlighting how human collaboration can be supported and how machine agents can be embedded into this environment. The applicability of this approach to sense-making has been highlighted with a brief example of ongoing work with open-source intelligence analysts from the Cardiff Crime and Security Research Institute. The experimental platform will be released as open source and can be used for many use cases that require human and machine integration for research from across DAIS ITA and beyond. Thank you for listening.